Here we are, floating through space on a small blue planet, convinced we understand the universe around us. We can see stars, galaxies, the gentle glow of distant nebulae. We've mapped cosmic structures, measured temperatures, calculated distances that stretch beyond imagination. And yet, according to our best scientific understanding, 95% of everything that exists is completely invisible to us. Not hidden behind clouds of dust or lurking in the shadows of black holes, but fundamentally undetectable by any instrument we've ever built. It's as if we've been living our entire lives in a house, confident we know every room, only to discover that most of the building exists in dimensions we cannot see or touch. Welcome back to another journey into the mysteries that shape our reality. I'm your guide through these quiet explorations of science and wonder, and tonight we're venturing into one of the most profound puzzles facing modern cosmology. If you're settling in for the evening, perhaps with a warm drink and a curious mind, you've found the perfect companion for this gentle dive into the cosmic unknown. Before we begin, I'd love to know where in the world you're joining me from tonight. Are you listening from a cozy apartment in Copenhagen as snow falls outside your window? Or perhaps from a quiet corner of a cafe in Seoul, watching the evening light fade? Drop a comment and let me know. There's something beautiful about imagining this community of curious minds scattered across the globe, all wondering about the same invisible universe. Now, when we say that 95% of the universe is missing, we're not talking about misplaced car keys or a cosmic filing error. We're talking about something far more fundamental. Everything you can see, touch, or measure, with even our most sophisticated instruments, represents just 5% of what actually exists. The atoms in your body, the stars in the night sky, the planets orbiting distant suns, all of it together makes up only a tiny fraction of the cosmic inventory. The rest, this overwhelming majority of reality, consists of two mysterious components that scientists have rather poetically named dark matter and dark energy. These aren't just gaps in our knowledge waiting to be filled by better telescopes. They represent substances and forces that appear to be woven into the very fabric of existence, yet remain as elusive as shadows cast by invisible objects. Let's begin with a simple question that leads to extraordinary implications. When you look up at the night sky and see the Milky Way stretching across the darkness, you're witnessing something that, by all rights, should have torn itself apart billions of years ago. Our galaxy, like every spiral galaxy we can observe, spins with a grace that defies the mathematics of visible matter. Picture a figure skater performing a perfect spiral, arms extended, rotating with elegant precision. Now imagine that this skater is spinning so fast that centrifugal force should fling her arms away from her body, yet somehow she maintains perfect form. This is essentially what galaxies are doing on a cosmic scale. When astronomers first began measuring the rotation speeds of galaxies in the 1960s and 70s, they expected to find a predictable pattern. Just as planets in our solar system move more slowly the farther they are from the Sun, they anticipated that stars at the edges of galaxies would orbit more slowly than those near the centre. The visible matter they could observe suggested this should be the case. Instead, they discovered something extraordinary. Stars at the outer edges of galaxies were moving just as fast as those closer to the galactic centre, sometimes even faster. It was as if the figure skaters' outstretched arms were somehow defying physics, maintaining their position despite forces that should tear them away. Take a moment to consider what this means. The Milky Way, our cosmic home, contains roughly 400 billion stars. Each one of these stars, including our own Sun, is racing around the galactic centre at speeds that should scatter them into the void. Yet here we are, billions of years after our galaxy formed, still held together in a magnificent spiral dance. The only way this makes sense is if there's far more mass in galaxies than we can see. Something invisible is providing the extra gravitational pull needed to keep these cosmic structures intact. This unseen mass doesn't interact with light in any way we can detect. It doesn't absorb photons, it doesn't emit them, and it doesn't reflect them. It's there only in the way it bends space and time, creating gravitational fields that hold the visible universe together. Scientists have named this mysterious substance dark matter, not because it's necessarily dark in color, but because it exists in a kind of cosmic shadow, detectable only through its gravitational effects on the matter we can observe. But here's where the story becomes even more intriguing. Dark matter isn't just a minor correction to our cosmic accounting. Current estimates suggest it makes up about 27% of the entire universe. That means for every atom of ordinary matter, every particle that makes up stars, planets, and people, there are roughly 5 times as much dark matter surrounding us, permeating space like an invisible ocean in which our visible universe floats. As extraordinary as dark matter is, it represents only part of our cosmic mystery. The remaining 68% of the universe consists of something even stranger: dark energy. To understand dark energy, we need to step back and consider one of the most surprising discoveries in the history of astronomy. In 1998, 2 independent teams of scientists were studying distant supernovae, using these cosmic explosions as standard candles to measure how the expansion of the universe was slowing down over time. Everyone expected the expansion to be decelerating. After all, gravity is an attractive force. Since the Big Bang, gravity should have been gradually slowing the universe's expansion, like a ball thrown upward, eventually slowing and falling back down due to Earth's gravitational pull. Instead, they found something that revolutionized our understanding of cosmic evolution. The universe isn't just expanding, the expansion is accelerating. It's as if that ball, instead of slowing down as it rises, suddenly begins speeding up, defying everything we thought we knew about gravity and motion. Imagine you're sitting in a quiet room and you notice that the walls are slowly, imperceptibly moving away from you. This might be curious, but not necessarily alarming. Now imagine that this movement begins to speed up. The walls start moving away faster and faster, and you realize that something is actively pushing the very fabric of space outward. This is essentially what's happening to our universe on the largest scales. This mysterious force driving the accelerating expansion has been named dark energy. Unlike dark matter, which clumps together and helps form cosmic structures, dark energy appears to be distributed uniformly throughout space. It's woven into the very vacuum, pushing every region of the universe away from every other region with increasing intensity. As you listen to this, take a breath and consider that you're floating in space that's filled with this invisible energy. Right now, between you and the wall nearest to you, dark energy is gently pushing outward. The effect is infinitesimally small on local scales, completely overwhelmed by other forces like gravity and electromagnetic interactions. But across cosmic distances, this gentle push adds up to the dominant force shaping the universe's fate. What makes dark energy particularly mysterious is that its density appears to remain constant, even as space expands. Imagine filling a balloon with air and then somehow having the same amount of air per unit volume, even as the balloon grows larger. This suggests that dark energy isn't simply some substance spread through space, but rather a fundamental property of space itself. The implications of living in a universe dominated by invisible components extend far beyond academic curiosity. These discoveries force us to confront a humbling truth about our place in the cosmic order. Consider this: every human who has ever lived, every thought that has ever been thought, every emotion felt, every work of art created, every scientific discovery made, all of it exists within that mere 5% of reality that consists of ordinary matter. We are not just small in terms of size compared to the universe. We are made of the rare stuff, the exceptional material that makes up only a tiny fraction of what exists. It's a bit like discovering that you've been living your entire life in a small, well-lit room, unaware that this room exists within a vast mansion that stretches in every direction, most of it in complete darkness. The familiar room with its visible furniture and walls represents the ordinary matter universe we know. The vast dark mansion surrounding it is the realm of dark matter and dark energy. This cosmic census problem, as scientists sometimes call it, reveals something profound about the nature of knowledge itself. We pride ourselves on being a scientific civilization, capable of sending spacecraft to other planets, splitting atoms, and peering deep into space with powerful telescopes. Yet the vast majority of reality remains as mysterious to us as it was to our ancestors who first looked up at the stars and wondered what they were seeing. But here's what's particularly fascinating. This invisible universe isn't separate from us. It's intimately connected to everything we can see and touch. Dark matter provides the gravitational scaffolding that allowed galaxies to form in the first place. Without it, the universe would be a thin soup of hydrogen and helium, too diffuse to ever condense into stars, planets, or the complex chemistry that makes life possible. Dark energy, meanwhile, is actively shaping the future of everything we can observe. Its accelerating push means that galaxies are moving away from each other at ever-increasing speeds. Billions of years from now, our local group of galaxies will be increasingly isolated as other galaxy clusters recede beyond the horizon of observability. As you contemplate this, notice how it might shift your perspective on what we consider real or important. The chair you're sitting in, the device you're using to listen to this, the air you're breathing, all of it exists within a vast context of invisible forces and substances that we're only beginning to understand. The hunt for dark matter has become one of the most intensive searches in the history of science. Deep underground, in abandoned mines and purpose-built laboratories, scientists have constructed incredibly sensitive detectors designed to catch dark matter particles in the act of colliding with ordinary matter. These experiments take place far below ground to shield them from cosmic rays and other interference that might mask the subtle signal of a dark matter interaction. Scientists are looking for the rarest of events, a dark matter particle, after travelling through space for perhaps billions of years, finally bumping into the nucleus of an ordinary atom in their detector. The challenge is extraordinary. Dark matter particles, if they exist as discrete entities, interact so weakly with ordinary matter that billions of them could be passing through your body every second without you ever noticing. It's like trying to catch raindrops that fall through your hands as if they were made of mist. Some researchers have proposed that dark matter might consist of particles called WIMPs, weakly interacting massive particles that were created in the early moments after the Big Bang. Others suggest axions, hypothetical particles, so light and weakly interacting that they would be almost ghost-like in their behavior. Still others explore the possibility of sterile neutrinos, particles that would interact even more weakly with ordinary matter than the already elusive neutrinos we know about. Despite decades of searching with increasingly sophisticated equipment, dark matter particles have remained stubbornly invisible. This persistent absence of direct detection has led some scientists to wonder whether we're looking for the right thing in the right way. The search for dark energy presents even greater challenges. Unlike dark matter, which might consist of particles we could potentially detect, dark energy appears to be a property of space itself. How do you build a detector for the vacuum of space? How do you capture and study something that might be woven into the fundamental structure of reality? Some theoretical physicists have proposed that dark energy might be the result of quantum fluctuations in empty space, a kind of cosmic background hum of particle pairs popping into and out of existence. Others suggest it might be evidence of extra dimensions of space that we cannot directly perceive, with our three-dimensional reality floating like a membrane in a higher dimensional space. The mystery deepens when we consider that the amount of dark energy in the universe appears to be precisely calibrated to allow for the formation of cosmic structures. Too little, and gravity would have prevented galaxies from forming. Too much, and the universe would have expanded so quickly that matter could never have clumped together into stars and planets. This apparent fine-tuning raises profound questions about the nature of the universe itself. Are we living in one of countless universes, each with different amounts of dark matter and dark energy, with ours being one of the rare ones suitable for complexity and life? Or is there some deeper principle we haven't yet discovered that explains why these invisible components have exactly the values they do? While we cannot directly detect dark matter particles or dark energy fields, their effects on the visible universe create some of the most spectacular phenomena in astronomy. Through gravitational lensing, dark matter reveals itself by bending and distorting light from distant galaxies, creating cosmic funhouse mirrors that stretch images into arcs and rings. When massive galaxy clusters, which contain enormous concentrations of dark matter, lie between us and more distant galaxies, they act like giant cosmic lenses. The gravitational field created by all this invisible mass bends the light from background galaxies, sometimes creating multiple images of the same object, or forming beautiful Einstein rings where a distant galaxy appears as a perfect circle of light around the lensing cluster. These gravitational lenses have allowed astronomers to create maps of dark matter distribution throughout the universe. Like detectives using fingerprints to track an invisible suspect, scientists can trace the location and concentration of dark matter by observing how it affects the light passing through it. Perhaps the most compelling evidence for dark matter comes from collisions between galaxy clusters. In 2006, astronomers observed the aftermath of a collision between two massive galaxy clusters in what's known as the Bullet Cluster. During this cosmic crash, the ordinary matter in the form of hot gas was slowed down by electromagnetic interactions and remained behind, while the dark matter passed through relatively unimpeded. Gravitational lensing observations revealed that the majority of the mass was located where the dark matter had passed through, separate from the visible matter that had been stripped away. This spatial separation provided direct evidence that something invisible and massive exists beyond the ordinary matter we can observe. It's as if two ghost armies had passed through each other in battle, and we could see their presence only by the way they disturbed the battlefield around them, even though the warriors themselves remained invisible. The effects of dark energy are visible on the grandest scales imaginable. By studying the light from distant supernova, astronomers can trace the expansion history of the universe over billions of years. They found that the expansion began accelerating about 5 billion years ago, roughly when our solar system was forming. This means that dark energy's influence has been shaping cosmic evolution for half the age of the universe. It's been stretching space, carrying galaxies away from each other, and determining the large-scale structure of everything we can observe. As we continue our search for understanding, take a moment to appreciate the extraordinary fact that invisible components of the universe reveal themselves through their interactions with the visible world. It's a reminder that reality extends far beyond what we can directly perceive, and that sometimes the most profound truths are hidden in the shadows cast by invisible things. The story of dark matter and dark energy is still being written, new telescopes coming online, more sensitive detectors being built deep underground, and theoretical breakthroughs yet to be made may finally solve these cosmic mysteries. Or they may reveal that the universe is even stranger than we currently imagine. But that's a story for another part of our journey. For now, as you sit in your small corner of the visible universe, remember that you're surrounded by invisible wonders, cosmic forces, and substances that shape everything you see, while remaining forever just beyond the reach of direct observation. If tonight's exploration of the invisible universe has sparked your curiosity about the hidden nature of reality, I think you'll find our previous journey equally fascinating. the quantum paradox that says reality only exists if you're watching. It's a gentle dive into how the act of observation itself might be fundamental to the very existence of the world around. The question becomes even more unsettling when we consider the timeline of cosmic discovery. For most of human history, we assume the universe was essentially static, unchanging, eternal. Then in the early 20th century, Edwin Hubble peered through his telescope and discovered that galaxies were racing away from us in all directions. The universe was expanding, but even this revolutionary insight paled in comparison to what came next. By the late 1990s, astronomers expected to find that this cosmic expansion was gradually slowing down, like a ball thrown upward, eventually succumbing to gravity. Instead, they discovered something that shattered our understanding of everything. The expansion was speeding up. Imagine throwing a ball into the air and watching it not only continue rising, but accelerate as it climbs higher and higher into the sky. This is essentially what our universe is doing on the larger scales. Something invisible is pushing against the very fabric of space, causing galaxies to flee from each other at ever-increasing speeds. This mysterious force, which we've named dark energy, doesn't just make up a small correction to our cosmic equations. It represents roughly 68% of everything that exists. Think about that for a moment. More than 2/3 of reality consists of something that actively pushes space apart, yet we have no idea what it actually is. To truly grasp how profoundly these invisible components shape our universe, let's take a journey backward through cosmic time. Imagine we could rewind the clock of creation, watching as the universe grows smaller, denser, and hotter until we reach those first moments after the Big Bang. In the earliest epochs, when the universe was a seething cauldron of energy and newly formed particles, dark matter began its silent work. While ordinary matter was too hot and energetic to clump together, dark matter particles, unaffected by the intense radiation, started forming the first gravitational wells in space. Picture these dark matter concentrations as invisible valleys in the landscape of space-time. As the universe cooled and ordinary matter finally became stable enough to respond to gravity, it naturally flowed into these pre-existing valleys, like water finding the lowest points in terrain. Without this invisible scaffolding, the universe would have remained a thin, uniform soup of hydrogen and helium. No galaxies would have formed. No stars would have ignited. No planets would have condensed from cosmic dust. The delicate chemistry that eventually gave rise to life would never have had the opportunity to begin. This means that your existence, the existence of Earth, of our solar system, of the Milky Way itself, all depended on the gravitational influence of substances we cannot see or touch. We are, quite literally, children of invisible forces. The role of dark energy in this cosmic story is equally profound, though it operates on different scales and timelines. For the first several billion years of the universe's existence, dark energy was present, but relatively weak compared to the gravitational pull of matter. During this era, gravity dominated, allowing structures to form and grow. But as the universe expanded and matter became more dilute, the influence of dark energy gradually strengthened. About 5 billion years ago, around the time our solar system was forming from a collapsing cloud of gas and dust, dark energy reached a tipping point. From that moment forward, it has been the dominant force shaping cosmic evolution. This transition from a matter-dominated to a dark energy-dominated universe marks one of the most significant phase changes in cosmic history. It's as if the universe switched from a phase where it was trying to pull itself together through gravity to a phase where it's actively pushing itself apart through some mysterious anti-gravitational force. One of the most beautiful ways to visualize the invisible universe is through computer simulations that model how dark matter behaves over cosmic time. These simulations reveal a hidden architecture that underlies everything we can observe, the cosmic web. Imagine the largest structures in the universe not as isolated islands of matter floating in empty space, but as glowing nodes connected by vast filaments of dark matter. These filaments stretch across hundreds of millions of light years, creating a three-dimensional web that spans the observable universe. Galaxy clusters form at the intersections of these filaments, like dewdrops collecting at the junctions of a spider's web. The Milky Way, along with our neighbouring galaxies, sits on one of these dark matter highways, carried along by gravitational currents we cannot directly perceive. Between the filaments lie vast cosmic voids, regions where both ordinary and dark matter are scarce. These voids, some spanning billions of light years across, represent the majority of the universe's volume. They are the closest thing to true emptiness that exists. Yet even here, dark energy continues its relentless work of pushing space apart. When astronomers map the distribution of galaxies across the sky, they're essentially tracing the visible portions of this invisible web. It's like looking at city lights from space and inferring the presence of highways and infrastructure that you cannot directly see but which clearly shape where people choose to build. This cosmic web is not static. It's constantly evolving, with dark matter flowing along the filaments like a slow-moving river system. Galaxies are gradually drawn toward the largest nodes, eventually merging and forming ever more massive structures. Meanwhile, dark energy works to stretch the web itself, making the filaments longer and thinner over cosmic time. Perhaps the most mind-bending aspect of dark energy is how it seems to violate our intuitive understanding of how forces work. In everyday experience, forces diminish with distance. The farther you are from something, the weaker its pull or push becomes. But dark energy appears to work in reverse. As the universe expands and space stretches, you might expect dark energy's influence to weaken, spread thin like butter on an ever-expanding slice of bread. Instead, the opposite happens. Dark energy's density remains constant, and its total effect grows stronger as space itself grows larger. This means that dark energy is not simply some substance filling space. It appears to be a fundamental property of space itself. Every cubic meter of vacuum, whether between galaxies or in the apparent emptiness of your room, contains the same amount of dark energy density. Consider what this means for the future of our universe. As space continues to expand and dark energy's influence grows stronger, galaxies will be carried away from each other at ever-increasing speeds. Eventually, galaxies beyond our local group will recede so quickly that their light will no longer be able to reach us. They will disappear beyond our cosmic horizon, leaving future astronomers in a universe that appears much lonelier than the one we observe today. Billions of years from now, an astronomer looking up at the night sky might see only the stars of their own galaxy, with all external galaxies having vanished into the darkness of accelerated expansion. They would inhabit a universe that appears static and isolated, with no evidence of the cosmic web or the Big Bang that brought everything into existence. This raises a humbling question. What might we be missing about our own cosmic environment? What evidence of larger structures or deeper truths might already have disappeared beyond our horizon, carried away by dark energy's inexorable push? Some of the most compelling evidence for dark matter comes from nature's most violent events. The collisions between galaxy clusters, these cosmic crashes, unfolding over hundreds of millions of years, create natural laboratories where the invisible universe reveals itself through its effects on ordinary matter. When two galaxy clusters collide, it's not like two solid objects smashing together. Galaxy clusters consist mostly of empty space, with individual galaxies separated by vast distances. During a collision, the galaxies themselves can pass through each other relatively unimpeded, like two swarms of fireflies intersecting in the night. But the hot gas that fills the space between galaxies experiences a very different fate. This gas, heated to millions of degrees and glowing in X-ray wavelengths, slams into itself during the collision, creating shockwaves and turbulence. The electromagnetic interactions slow this gas down, causing it to lag behind as the collision proceeds. Meanwhile, the dark matter, which interacts only through gravity, passes through the collision zone largely unaffected. It's as if two ghost armies march through each other without slowing, while the visible soldiers they command become entangled in battle. The result is a spatial separation between where most of the mass is located, traced by gravitational lensing, and where most of the visible matter ends up, revealed by X-ray observations. This separation provides some of the strongest direct evidence that dark matter exists as something distinct from ordinary matter. The Bullet cluster, located about 3.8 billion light-years away, represents the most famous example of this phenomenon. When astronomers studied the aftermath of this cluster collision, they found that roughly 90% of the total mass had passed through the collision and continued moving, while only 10% remained behind in the form of hot, glowing gas. The cosmic microwave background, that faint afterglow of the Big Bang that fills all of space, carries within its subtle patterns the fingerprints of dark matter and dark energy. This ancient light, which has been travelling for nearly 14 billion years, provides us with a baby picture of the universe when it was only 380,000 years old. At first glance, this background radiation appears remarkably uniform in all directions, but careful measurement reveals tiny temperature fluctuations, variations of just a few millionths of a degree. These minute differences represent the seeds from which all cosmic structure would eventually grow. The pattern of these fluctuations tells a detailed story about the invisible components of our universe. The size and distribution of hot and cold spots depend critically on how much dark matter was present in the early universe and how it was distributed. By analysing these patterns with extraordinary precision, cosmologists can determine not just that dark matter exists, but exactly how much of it fills the cosmos. The cosmic microwave background also reveals evidence of dark energy's influence, though more subtly. The geometry of space itself affects how light travels across cosmic distances. If space is curved by dark energy in particular ways, this curvature leaves measurable imprints on the patterns we observe in the background radiation. These observations have allowed scientists to construct what they call the Standard Model of Cosmology. According to this model, our universe consists of about 5% ordinary matter, 27% dark matter, and 68% dark energy. It's a precise cosmic recipe for everything that exists, yet we don't truly understand what most of the ingredients actually are. One of the most intriguing theoretical approaches to understanding dark energy involves the quantum properties of empty space itself. According to quantum mechanics, what we call empty vacuum is never truly empty. It seethes with virtual particles that pop into existence and annihilate each other in timeframes so brief that they cannot be directly observed. This quantum foam, as it's sometimes called, should contribute energy to the vacuum of space. In principle, this vacuum energy could be what we observe as dark energy, providing the mysterious force that drives cosmic acceleration. However, when physicists attempt to calculate how much energy the quantum vacuum should contain, they arrive at a number that is larger than the observed dark energy density by a factor of 10 to the power of 120. This represents perhaps the worst prediction in the history of physics, off by more than 100 orders of magnitude. This enormous discrepancy, known as the cosmological constant problem, suggests that either our understanding of quantum mechanics is fundamentally incomplete, or there's some unknown mechanism that cancels out most of the vacuum energy, leaving only the tiny amount we observe as dark energy. Some theorists have proposed that dark energy might not be a constant property of space, but rather a slowly evolving field that changes over cosmic time. This hypothetical field, sometimes called quintessence, after the classical fifth element, could explain why dark energy's influence has grown stronger as the universe has aged. Others suggest that our observations of cosmic acceleration might indicate not the presence of dark energy, but rather a breakdown in our understanding of gravity itself on cosmic scales. Perhaps Einstein's theory of general relativity, which has passed every test in our local cosmic neighborhood, begins to behave differently when applied to the universe as a whole. The hunt for dark matter has intensified dramatically in recent decades, with experiments operating deep underground, in space, and at the world's most powerful particle accelerators. Each approach offers a different window into the invisible realm that surrounds us. Underground detectors, shielded from cosmic radiation by kilometers of rock, wait patiently for dark matter particles to collide with ordinary matter. These experiments must be extraordinarily sensitive, capable of detecting the tiny energy deposited when a dark matter particle strikes an atomic nucleus. Some use tanks of liquid xenon, cooled to incredibly low temperatures, while others employ crystals that would emit a faint flash of light if struck by the right kind of particle. Space-based telescopes search for the indirect signatures of dark matter interactions. If dark matter particles occasionally collide and annihilate each other, they might produce high-energy gamma rays or other radiation that could be detected from orbit. The Fermi Gamma Ray Space Telescope and other instruments continuously scan the sky for these potential dark matter signals. Meanwhile, particle accelerators attempt to create dark matter in controlled conditions. If dark matter particles can be produced in high-energy collisions, they might reveal themselves through the energy they carry away from the collision point, leaving behind a characteristic missing energy signature. Despite decades of searching with increasingly sophisticated technology, dark matter particles have remained frustratingly elusive. This absence of direct detection has led some scientists to propose more exotic possibilities. Perhaps dark matter exists in a hidden sector of physics, interacting with our world only through gravity and other forces we haven't yet discovered. The search for dark energy faces even greater challenges, since it appears to be woven into the fabric of space itself, rather than consisting of discrete particles that could potentially be detected. Future space missions will map the universe's expansion history with unprecedented precision, searching for clues about dark energy's true nature in the subtle details of how cosmic acceleration has changed over time. As we continue this cosmic detective story, remember that you're living through one of the most exciting periods in the history of astronomy. We stand at the threshold of potentially revolutionary discoveries about the nature of reality itself. The invisible universe that surrounds us may be on the verge of revealing its secrets, or it may surprise us with mysteries even deeper than we currently imagine. There's something almost poetic about the way the invisible universe organizes itself. While we've been searching for dark matter particles in underground laboratories and scanning space for gamma rays, nature has been quietly painting portraits of the unseen with light itself. When you look at images from the Hubble Space Telescope showing distant galaxies warped and stretched into ethereal arcs, you're witnessing dark matter's artistic signature. These gravitational lenses, as astronomers call them, transform invisible mass into visible distortions, like shadows cast by objects we cannot see. The most remarkable aspect of these cosmic mirages is how they reveal the three-dimensional architecture of dark matter across vast distances. Imagine trying to map the shape of an invisible mountain by watching how it bends the light from a campfire on the other side. This is essentially what gravitational lensing allows us to do on cosmic scales. Through careful analysis of these distorted galaxy images, astronomers have created maps of dark matter distribution, stretching back billions of years into cosmic history. What they've discovered is a universe that looks remarkably different when viewed through the lens of invisible matter. The cosmic web we discussed earlier isn't just a theoretical construct, it's a real, measurable structure that we can trace through its gravitational effects. Dark matter filaments, some stretching across hundreds of millions of light years, connect galaxy clusters in a vast network that spans the observable universe. But here's where the mystery deepens. Computer simulations of dark matter predict that these cosmic structures should be filled with countless smaller clumps and substructures. Every galaxy should be surrounded by hundreds of smaller dark matter halos, invisible satellites orbiting like ghostly moons. Yet when astronomers count the number of small satellite galaxies around the Milky Way, they find far fewer than the simulations predict. This discrepancy, known as the missing satellites problem, suggests that either our understanding of dark matter is incomplete, or the relationship between dark matter and visible galaxy formation is more complex than we imagined. As we contemplate the nature of dark energy, we encounter perhaps the most profound question in modern cosmology. Why is the universe accelerating now? The timing of cosmic acceleration appears to be remarkably coincidental, beginning roughly when the universe was about half its current age. For billions of years after the Big Bang, gravity dominated the cosmic stage. Matter clumped together, forming the first stars, galaxies, and larger structures. During this era, dark energy was present but relatively weak, like a gentle breeze barely noticed against the stronger gravitational winds. But as the universe expanded and matter became more dilute, the balance of cosmic forces began to shift. Dark energy, whose density appears to remain constant even as space stretches, gradually gained the upper hand. The transition from deceleration to acceleration represents one of the most significant phase changes in cosmic history. What makes this timing so puzzling is that we happen to be living during this cosmic transition. If dark energy had begun dominating much earlier, structures like galaxies and stars might never have had the chance to form. If it had begun dominating much later, we might not yet have detected its effects. This apparent coincidence has led some cosmologists to propose what they call the anthropic principle. Perhaps we observe these particular values of dark matter and dark energy precisely because they are the conditions necessary for observers like ourselves to exist. In a multiverse containing countless variations, only universes with the right balance of invisible components would give rise to complexity and consciousness. Yet this explanation, while mathematically consistent, leaves many scientists unsatisfied. It suggests that the fundamental constants of nature might be determined not by deep physical principles, but by the requirement that conscious observers must exist to measure them. The search for understanding has led physicists to examine the very foundations of space and time themselves. At the smallest scales, quantum mechanics tells us that empty space is not truly empty, but filled with virtual particles that constantly appear and disappear in pairs. These quantum fluctuations create what physicists call zero-point energy, a background hum of activity that permeates every cubic centimetre of space. In principle, this quantum vacuum energy could be the source of the dark energy we observe, driving cosmic acceleration. However, when theoretical physicists attempt to calculate the amount of energy contained in the quantum vacuum, they encounter one of the most spectacular failures in the history of science. Their calculations predict a vacuum energy density that exceeds observations by more than 100 orders of magnitude. To put this discrepancy in perspective, imagine predicting that a teaspoon of space contains enough energy to power all the stars in the observable universe for trillions of years, when in reality it contains barely enough energy to lift a grain of sand. This enormous mismatch suggests that something fundamental is missing from our understanding of how quantum mechanics and gravity interact. Some theorists have proposed that most of the quantum vacuum energy might be cancelled out by some unknown mechanism, leaving only the tiny residue we observe as dark energy. Others suggest that our understanding of space and time at the smallest scales might be fundamentally incorrect. The quest to resolve this paradox has led to some of the most exotic theories in modern physics. String theory, which proposes that the fundamental constituents of reality are tiny vibrating loops rather than point particles, offers potential mechanisms for cancelling vacuum energy. Loop quantum gravity suggests that space itself might be quantized at the smallest scales, made up of discrete units that could naturally limit vacuum fluctuations. Nature provides us with experimental conditions that we could never recreate in earthbound laboratories. The collision between galaxy clusters, unfolding over hundreds of millions of years, allows us to test our theories of dark matter under the most extreme conditions imaginable. When the Bullet cluster was first studied in detail, it provided what many consider the smoking gun evidence for dark matter's existence. The collision had separated the visible matter, in the form of hot gas glowing in X-rays, from the invisible matter that could only be detected through gravitational lensing. But subsequent observations of other cluster collisions have revealed a more complex picture. Some collisions show the expected separation between dark and ordinary matter, while others display more puzzling behaviors. In a few cases, dark matter appears to lag behind the galaxies themselves, suggesting interactions we don't fully understand. These observations have led to increasingly sophisticated theories about dark matter's properties. Perhaps dark matter particles interact not only through gravity, but through their own hidden forces. Maybe there's an entire dark sector of physics, complete with dark atoms, dark chemistry, and even dark planets orbiting dark stars in invisible solar systems. The possibility of a rich dark sector opens up extraordinary questions about the nature of complexity in the universe. Could there be forms of organization and even life based on dark matter that remain completely invisible to us? Might we be sharing our cosmic neighborhood with civilizations we cannot see or detect? The cosmic microwave background radiation, that faint whisper from the universe's infancy, continues to yield secrets about the invisible components that shape our reality. As our instruments become more sensitive, we can detect subtler and subtler variations in this ancient light. Recent observations have revealed polarization patterns in the cosmic microwave background that carry information about the earliest moments after the Big Bang. These swirling patterns, called B-modes, might preserve evidence of cosmic inflation, the rapid expansion that occurred in the universe's first fraction of a second. If confirmed, these observations would provide direct evidence for one of the most extraordinary ideas in cosmology, that our entire observable universe began as a quantum fluctuation, smaller than a subatomic particle, that was stretched to cosmic proportions by inflationary expansion. The implications extend far beyond our understanding of the early universe. Inflation theory suggests that our observable universe might be just one bubble in an infinite multiverse, with countless other bubble universes existing beyond our cosmic horizon. Each bubble might have different amounts of dark matter and dark energy, different physical constants, perhaps even different numbers of spatial dimensions. In this view, the invisible universe we're trying to understand represents just one variation in an endless symphony of possible realities. The values of dark matter and dark energy that allow for the formation of galaxies, stars, and life might be rare cosmic accidents, flukes of cosmic evolution that occur in only a tiny fraction of all possible universes. As we peer into the cosmic future, shaped by dark energy's accelerating influence, we encounter a universe that will become increasingly lonely and cold. The gentle push that currently drives galaxies apart will grow stronger over time, eventually overwhelming even the gravitational bonds that hold galaxy clusters together. Billions of years from now, the night sky will tell a very different story. Galaxies beyond our local group will have receded so far and so fast that their light can no longer reach us. Future astronomers will inhabit a universe that appears much smaller and more isolated than the rich cosmic web we observe today. This cosmic isolation raises profound questions about the nature of knowledge and discovery. How much of the universe's history and structure might already be hidden beyond our cosmic horizon, carried away by eons of accelerating expansion? What evidence of larger patterns or deeper truths might we never have the chance to observe. Yet even as dark energy carries distant galaxies beyond our reach, it continues to provide us with opportunities for discovery. New space-based telescopes, more sensitive than any built before, will map the expansion history of the universe with unprecedented precision. These observations might finally reveal whether dark energy is truly constant or whether it changes over cosmic time. Ground-based surveys will catalogue billions of galaxies, tracing the cosmic web in ever greater detail. These maps might reveal subtle patterns that could distinguish between different theories of dark matter and dark energy, finally providing the clues needed to understand the invisible universe. Perhaps the most profound lesson from our exploration of the invisible universe is how it reshapes our understanding of humanity's place in the cosmic order. We are not simply small creatures on a small planet orbiting an average star. We are made of the exceptional material, the rare 5% of reality that interacts with light and forms the complex structures we call atoms, molecules, and life. This realization carries both humbling and inspiring implications. On one hand, it suggests that we are even more cosmically insignificant than we previously imagined. The vast majority of reality remains invisible to us, operating according to rules we're only beginning to glimpse. On the other hand, it suggests that ordinary matter, the stuff of stars and planets and people, represents something genuinely special in the cosmic inventory. The atoms in your body, forged in the hearts of ancient stars, are participants in the rare physics of electromagnetic interactions and chemical complexity. The invisible universe that surrounds us is not separate from our existence, but intimately connected to it. Dark matter provided the gravitational scaffolding that allowed galaxies to form. Dark energy shapes the cosmic environment in which stars are born and die. Without these invisible components, the universe would be a very different place, perhaps too simple and uniform to give rise to the rich chemistry of life. As you contemplate your place in this vast, mostly invisible cosmos, consider that your existence represents a kind of cosmic miracle, not because you were specially created, but because you emerged from the complex interplay between visible and invisible forces that have been shaping the universe for nearly 14 billion years. As our journey through the invisible universe draws toward a close, we find ourselves confronting the limits of current human knowledge, while simultaneously marveling at how far our understanding has come. From the first hints of missing mass in galaxy rotation curves to the revolutionary discovery of cosmic acceleration, each breakthrough has revealed new depths to the mystery surrounding us. The story of dark matter and dark energy is far from over. Underground detectors continue their patient vigil, waiting for the first confirmed interaction with a dark matter particle. Space telescopes map the cosmic web with increasing precision, searching for clues about the nature of invisible matter. Theoretical physicists work to reconcile quantum mechanics with gravity, seeking to understand how the vacuum of space itself might drive cosmic acceleration. Each new observation, each refined measurement, each theoretical insight brings us closer to understanding the invisible universe, even as it reveals new questions we hadn't thought to ask. This is the nature of scientific discovery. Each answer illuminates new mysteries. Each solution opens doors to deeper puzzles. The search for dark matter and dark energy represents more than just an academic exercise in cosmic accounting. It touches on the most fundamental questions we can ask about reality itself. What is the universe made of? How did it come to be? What forces shape its evolution? What is our place within the cosmic story? As you continue your own journey of curiosity and wonder, remember that you are living through one of the most exciting periods in the history of human discovery. The invisible universe that surrounds us may be on the verge of revealing its secrets, or it may surprise us with mysteries even stranger and more beautiful than we currently imagine. The 95% of reality that remains hidden from our direct perception, continues to beckon, challenging us to expand our understanding, refine our instruments, and imagine new possibilities for what the universe might be. In that ongoing quest to illuminate the invisible, we find not just scientific knowledge, but a profound sense of connection to the vast, mysterious cosmos that is our home. The most ingenious aspect of hunting for invisible matter isn't the technology itself, but the detective work required to interpret what we find. When scientists first began searching for dark matter particles, they expected a straightforward process: build a detector, wait for collisions, count the results. Reality, as usual, proved far more subtle. Consider the challenges facing researchers working thousands of feet underground in abandoned mines. They've created some of the most sensitive instruments ever built, capable of detecting the energy deposited by a single atomic nucleus recoiling from an invisible collision, yet they must distinguish this faint signal from a constant background of other particles, cosmic rays that have travelled through miles of rock, and even the radioactive decay of trace elements in their own equipment. It's like trying to hear a whisper in a crowded restaurant while wearing noise-cancelling headphones that aren't quite perfect. Every click, every electronic hum, every stray vibration becomes a potential false alarm that could mask the signal they're seeking. The underground laboratories themselves represent marvels of engineering and determination, carved into mountains or built in caverns that haven't seen sunlight for millions of years. These facilities exist in some of the quietest environments on Earth. Scientists have learned to worry about things that would never occur to most people: the gamma rays emitted by concrete walls, the cosmic ray showers that penetrate even the deepest mines, the seasonal variations in particle backgrounds caused by changes in the atmosphere miles above. Some experiments cool their detectors to temperatures colder than deep space, creating conditions so pristine that a single unwanted interaction can contaminate months of data. Others surround their instruments with layers of shielding made from materials that were forged before the atomic age, when the atmosphere contained fewer artificial radioactive isotopes. While the search for dark matter focuses on catching individual particles in the act, understanding dark energy requires a completely different approach. You cannot build a detector for the expansion of space itself. Instead, scientists must become cosmic archaeologists, reading the history of universal expansion in the light from distant objects. The most powerful tool in this investigation comes from studying supernovae, stellar explosions so bright they can be seen across billions of light-years of space. These cosmic beacons serve as standard candles, objects whose intrinsic brightness is known, allowing astronomers to determine their distance by measuring how faint they appear from Earth. But here's where the detective work becomes truly remarkable. By comparing a supernova's distance with how fast it's moving away from us, revealed by the redshift of its light, scientists can reconstruct how the universe's expansion has changed over cosmic time. Each distant supernova represents a data point in the universe's biography, a chapter in the story of how space itself has evolved. The pattern that emerges from these observations tells a tale that no one expected. For the first several billion years after the Big Bang, the expansion of the universe was indeed slowing down, just as theoretical predictions suggested. Gravity was winning the cosmic tug-of-war, gradually applying the brakes to the outward rush of matter and energy. Then about 5 billion years ago, something changed. The cosmic deceleration stopped, paused for a moment, and then reversed into acceleration. It was as if the universe took a deep breath and began pushing against itself, stretching space at an ever-increasing rate. This transition point, occurring roughly when our solar system was condensing from a cloud of gas and dust, marks one of the most significant moments in cosmic history. From that point forward, dark energy has been the dominant influence shaping the universe's evolution, and its grip continues to strengthen with each passing eon. One of the most puzzling aspects of our current cosmic situation is the timing. Why are we living during the era when dark energy is just beginning to dominate the universe? This question, known as the coincidence problem, suggests that either we are extraordinarily fortunate in our cosmic timing, or there's something fundamental about this epoch that we don't yet understand. Consider the cosmic timeline. If dark energy had begun dominating much earlier in the universe's history, matter would never have had the chance to clump together into galaxies and stars. The accelerating expansion would have torn apart any structures before they could form, leaving the universe as a thin, cold soup of isolated particles. If dark energy had remained weak for much longer, we might be living in a very different kind of cosmos, one where gravity continued to dominate and the universe eventually collapsed back in on itself in a cosmic crunch. The delicate balance that allows for both structure formation and eventual acceleration appears to be calibrated with remarkable precision. Some cosmologists have suggested that this apparent fine-tuning might be explained by the anthropic principle. Perhaps we observe these particular values precisely because they're the conditions necessary for observers to exist. In a multiverse containing countless variations, only those universes with the right balance of dark matter and dark energy would give rise to complexity and consciousness. Yet this explanation, while mathematically consistent, raises as many questions as it answers. It implies that the fundamental constants of nature might be determined not by deep physical laws, but by the requirement that conscious beings must exist to measure them. It's a profoundly philosophical interpretation of what appears to be a purely physical phenomenon. As dark energy continues to accelerate the expansion of space, it creates what cosmologists call an information horizon. Galaxies that are visible to us today will eventually recede so quickly that their light can no longer bridge the growing gulf of space between us. When this happens, information about those regions of the universe will be permanently lost to us. This process is already underway. There are galaxies we can observe today whose most recent light is already doomed never to reach us. We see them as they were billions of years ago, frozen in cosmic time at the moment when their light began its journey toward Earth. But any new developments in those galaxies, any stars that form or explode, any changes in their structure or composition, will remain forever unknown to us. The implications extend far beyond simple observational limitations. As more and more of the universe disappears beyond our cosmic horizon, future civilizations will inhabit a cosmos that appears increasingly isolated and static. They will lose access to crucial evidence about the Big Bang, cosmic evolution, and the large-scale structure of reality. Imagine an astronomer a trillion years in the future, living in a universe where only the local group of galaxies remains visible. With no external galaxies to observe, no cosmic microwave background to study, and no evidence of universal expansion, how would they deduce that their universe had a beginning? How would they discover the existence of dark matter and dark energy? This raises a humbling question about our own cosmic situation. What evidence about the nature of reality might already have disappeared beyond our horizon, carried away by billions of years of accelerating expansion? Are we missing crucial pieces of the cosmic puzzle simply because we arrived on the scene too late to observe them? Understanding the invisible universe requires thinking across scales that stretch from the quantum realm to cosmic horizons. Dark matter particles, if they exist, might be smaller than protons, yet influence the formation of galaxy clusters spanning hundreds of millions of light years. Dark energy operates uniformly throughout space, yet drives changes that unfold over billions of years. This vast range of scales creates unique challenges for both observation and theory. The same dark matter that determines whether a galaxy will form must also account for the subtle gravitational effects measured in underground laboratories. The dark energy that drives cosmic acceleration must be consistent with quantum field theories that describe the behavior of virtual particles in empty space. Recent advances in computational cosmology have allowed scientists to simulate the evolution of the universe across these enormous ranges of scale and time. These simulations begin with the quantum fluctuations present in the early universe and follow them as they grow into the cosmic web we observe today. The results are both beautiful and mysterious. The simulations successfully reproduce many features of the observed universe: the distribution of galaxies, the structure of the cosmic web, the patterns in the cosmic microwave background. Yet they also predict phenomena we haven't yet observed, such as the countless small dark matter halos that should surround every galaxy. These discrepancies between simulation and observation hint that our understanding remains incomplete. Perhaps dark matter interacts with itself in ways we haven't accounted for. Maybe the relationship between dark matter and ordinary matter is more complex than we assumed. Or perhaps we're missing entire categories of physics that operate on intermediate scales. At the smallest scales imaginable, quantum mechanics describes a universe that bears little resemblance to our everyday experience. Virtual particles pop into existence and annihilate each other in time frames so brief they cannot be directly observed. Empty space buzzes with zero-point energy, a background activity that pervades every cubic centimetre of the cosmos. This quantum foam, as physicists call it, might hold the key to understanding dark energy. If the vacuum of space contains energy, as quantum mechanics suggests, this energy would act like a cosmological constant, driving the accelerated expansion we observe. The problem is that calculations of vacuum energy yield results that are wrong by more than 100 orders of magnitude. This spectacular failure of theoretical prediction suggests that something fundamental is missing from our understanding of how quantum mechanics and gravity interact. Perhaps most of the vacuum energy is cancelled out by some unknown mechanism. Maybe our theories break down when applied to cosmic scales. Or possibly the vacuum energy we calculate doesn't actually contribute to the expansion of space in the way we expect. Some of the most exotic theories in modern physics have emerged from attempts to resolve this paradox. String theory proposes that the fundamental constituents of reality are tiny vibrating loops that exist in dimensions beyond the three we experience. Extra-dimensional theories suggest that gravity might leak into hidden dimensions, weakening its apparent strength in our three-dimensional world. These ideas push the boundaries of both mathematics and imagination. They describe universes with 10 or 11 dimensions, where particles are manifestations of geometric shapes in higher dimensional spaces, and where the laws of physics we observe emerge from deeper symmetries we cannot directly perceive. The next decade promises to bring unprecedented advances in our ability to map and understand the invisible universe. New space telescopes, more sensitive than any previously built, will survey billions of galaxies with extraordinary precision. Ground-based observatories equipped with adaptive optics will peer deeper into space than ever before, revealing the cosmic web test, our theories of dark matter and dark energy within exquisite detail. These observations will unprecedented rigor. If dark energy is truly constant, the expansion history of the universe should follow specific mathematical predictions. If dark matter consists of particular types of particles, they should leave characteristic signatures in the distribution of cosmic structures. Perhaps most exciting is the possibility that these observations might reveal phenomena we haven't yet imagined. The history of astronomy is filled with surprises, discoveries that forced scientists to completely revise their understanding of cosmic reality. The detection of cosmic acceleration in 1998 represents just the most recent example of how observations can overturn theoretical expectations. Future surveys will map the positions and motions of galaxies across cosmic time with such precision that even subtle effects of dark matter and dark energy should become visible. These measurements might finally distinguish between competing theories, revealing whether dark energy represents a fundamental property of space or something more exotic. The underground search for dark matter particles continues to push toward ever greater sensitivity. Next-generation detectors will be able to detect interactions so rare that they might occur only once per year in tons of target material. These experiments represent perhaps humanity's best chance of directly confirming the existence of dark matter particles. The discovery that 95% of the universe consists of invisible components has profound implications that extend far beyond physics and astronomy. It challenges our most basic assumptions about the nature of reality and our ability to understand it through direct observation. For most of human history, we assumed that seeing was believing. The scientific revolution was built on the principle that nature reveals its secrets through careful observation and measurement. Yet dark matter and dark energy suggest that the most important aspects of reality might be fundamentally unobservable, detectable only through their indirect effects on the small fraction of the universe we can see. This situation forces us to confront deep questions about the nature of knowledge itself. If we can never directly observe the vast majority of reality, what does it mean to truly understand the universe? Are we condemned to forever glimpse only shadows of a larger truth, like prisoners in Plato's cave watching projections on the wall? Yet there's something remarkably hopeful about our current situation. Despite being made of the rare matter that represents only 5% of cosmic reality, we've managed to deduce the existence and properties of the invisible majority. Through careful observation, mathematical reasoning, and theoretical insight, we've mapped the cosmic web of dark matter and measured the acceleration driven by dark energy. This achievement suggests that the universe, however strange and mysterious, operates according to comprehensible principles. Even if we cannot see dark matter particles directly, they still obey the laws of gravity. Even if dark energy remains mysterious, its effects follow mathematical patterns we can measure and predict. Living in a universe dominated by invisible components might initially seem to diminish our significance. We are not only small in size compared to cosmic scales, but we're made of the exceptional material that represents only a tiny fraction of what exists. Our entire observable reality floats like a small island in an ocean of the unseen. Yet this perspective might also be profoundly liberating. If the universe is far stranger and more mysterious than we ever imagined, it suggests that reality contains depths we're only beginning to explore. The invisible universe doesn't diminish the wonder of existence. It amplifies it beyond all previous conception. Consider that the atoms in your body, forged in the hearts of ancient stars, are participants in the rare physics of electromagnetic interactions and chemical complexity. The consciousness that allows you to contemplate these mysteries emerge from the intricate dance between ordinary and dark matter that has been unfolding for nearly 14 billion years. You exist at the intersection of the visible and invisible, shaped by forces you cannot see, but which determine the very possibility of your existence. Dark matter provided the gravitational scaffolding that allowed galaxies to form. Dark energy shapes the cosmic environment in which stars are born and die. Without these invisible components, the universe would be too simple and uniform to give rise to the rich chemistry of life. This realization transforms our understanding of what it means to be human in a cosmic context. We are not separate from the invisible universe, but intimately connected to it. Our existence depends on the delicate balance between forces we can observe and those we cannot, between the matter that forms our bodies and the dark matter that holds our galaxy together. As we reach the end of our exploration, we find ourselves standing at the shore of an infinite ocean of mystery. The invisible universe that surrounds us continues to beckon, challenging us to expand our understanding, refine our instruments, and imagine new possibilities for what reality might be. The story of dark matter and dark energy is far from over. Each new observation, each theoretical breakthrough, each technological advance brings us closer to understanding the invisible majority, while revealing new questions we hadn't thought to ask. This is the nature of scientific discovery. Each answer illuminates new mysteries. Each solution opens doors to deeper puzzles. The search for the invisible universe represents more than just an academic exercise in cosmic accounting. It touches on the most fundamental questions we can ask about reality itself. What is the universe made of? How did it come to be? What forces shape its evolution? What is our place within the cosmic story? These questions drive us to build ever more sensitive detectors, to peer deeper into space with increasingly powerful telescopes, to develop theories that stretch the boundaries of human imagination. In pursuing answers to these cosmic mysteries, we push the limits of technology, mathematics, and philosophical understanding. The 95% of reality that remains hidden from our direct perception continues to shape everything we can observe. It determines the formation of galaxies, drives the acceleration of cosmic expansion, and creates the gravitational architecture that allows complex structures to exist. Understanding this invisible universe isn't just about satisfying scientific curiosity, it's about comprehending the fundamental nature of the cosmos we inhabit. As you continue your own journey of wonder and discovery, remember that you are living through one of the most extraordinary periods in human history. We stand on the brink of potentially revolutionary discoveries about the nature of reality itself. The invisible universe may be preparing to reveal its secrets, or it may surprise us with mysteries even stranger and more beautiful than we currently imagine. In either case, the search continues. In laboratories buried deep underground, in observatories perched on mountaintops, in the mathematical equations of theoretical physicists, and in the quiet moments of contemplation when we gaze up at the night sky and wonder about the vast, invisible cosmos that surrounds us. The missing 95% of the universe remains the greatest mystery of our time, a cosmic riddle that challenges everything we think we know about reality. And in that ongoing quest to illuminate the invisible, we find not just scientific knowledge, but a profound sense of connection to the vast, mysterious cosmos that is our home. The invisible universe awaits. Its secrets may be closer to discovery than we imagine, hidden in the next observation, the next theoretical insight, the next moment of clarity when the pieces of the cosmic puzzle finally begin to fall into place. Until then, we continue to search, to wonder, and to marvel at the extraordinary mystery of existence itself. In the depths of space, there exists a phenomenon so subtle, so delicate, that it took humanity centuries to notice it was happening at all. Imagine tending a garden where the flowers grow so slowly that their movement is imperceptible to the naked eye. Yet over seasons and years, their quiet transformation reshapes the entire landscape. This is how dark energy works its influence on the cosmos, a gentle but relentless gardener, sculpting the universe, one moment at a time. The cosmic microwave background radiation, that ancient whisper we discussed earlier, carries within its patterns the fingerprints of this cosmic gardening. When scientists first mapped these temperature variations with extraordinary precision, they discovered something unexpected embedded in the data. The fluctuations weren't random noise from the early universe. They were organized, structured, almost musical in their mathematical harmony. These patterns tell us about the seeds from which everything visible eventually grew, but they also reveal the invisible hand that guided this growth. Dark matter's gravitational pull created the valleys where ordinary matter could collect. Dark energy's gentle push determined how quickly space expanded around these growing structures. Together, they composed a symphony of cosmic evolution that played out over billions of years. Picture the early universe as a vast concert hall filled with the softest possible music. The notes were there, barely audible, encoded in tiny variations of temperature and density. Over cosmic time, These whispered melodies grew into the thunderous crescendo of galaxy formation, star birth, and planetary systems. Yet even now, in the relative quiet between movements, that original music continues to play, still shaping the space around us. Perhaps the most counterintuitive aspect of dark energy is how it defies our everyday understanding of what it means for something to exist. We're accustomed to thinking of energy as something that can be contained, measured, transferred from one place to another. The gasoline in your car, the electricity powering your lights, the chemical energy stored in your muscles, all of these follow familiar rules about conservation and transformation. Dark energy operates by entirely different principles. As space expands and the universe grows larger, you might expect this mysterious energy to become diluted, spread thinner like ink dropping into an expanding pool of water. Instead, the energy density remains constant. Every new cubic meter of space that comes into existence through cosmic expansion arrives already filled with the same amount of dark energy as every other cubic meter. This means that the total amount of dark energy in the universe is constantly increasing. Not because it's flowing in from somewhere else, not because it's being created by some cosmic factory, but because it appears to be an intrinsic property of space itself. The vacuum of empty space, rather than being truly empty, carries this invisible burden of energy that drives everything apart. Consider what this implies about the nature of nothingness. The space between galaxies, which appears to contain absolutely nothing, actually seethes with this mysterious energy. The gap between atoms in your body, the apparent emptiness between the stars, even the vacuum inside the most sophisticated laboratory chambers, all of it filled with dark energy, gently pushing outward. In quantum mechanics, we've learned that empty space is never truly empty, filled instead with virtual particles that appear and disappear faster than we can measure. But dark energy suggests something even stranger. It implies that the vacuum itself has weight, that nothingness itself participates in the gravitational dance that shapes cosmic evolution. Every photon that reaches your eyes carries with it a story of its journey through the invisible universe. Light from distant galaxies doesn't simply travel through empty space. It navigates through dark matter halos, around massive cosmic structures, through regions where dark energy stretches the fabric of space itself. By the time it arrives at your telescope or your retina, it bears the accumulated evidence of every invisible encounter along the way. Astronomers have become expert archaeologists of light, reading these photonic histories to reconstruct the invisible landscape through which they passed. When light travels near a concentration of dark matter, its path bends slightly due to gravitational lensing. This bending creates distortions in the images we observe, subtle warping that reveals the presence of invisible mass. But the effects go deeper than simple image distortion. Light from very distant objects has been traveling for so long that it carries information about how the universe has changed during its journey. A photon that left a galaxy 10 billion years ago began its trip when the universe was smaller, denser, and dominated by different forces than it is today. As this ancient light travelled through expanding space, dark energy gradually stretched its wavelength, shifting it toward the red end of the spectrum. The amount of this redshift tells us not only how far the light has travelled, but how much the universe has expanded during its journey. By comparing light from objects at different distances, we can trace the entire expansion history of the cosmos. This archaeological approach has revealed one of the most profound discoveries in modern cosmology. The expansion of space hasn't been uniform throughout cosmic history. For the first several billion years after the Big Bang, the expansion was slowing down as gravity tried to pull everything back together. Then, roughly 5 billion years ago, dark energy gained the upper hand, and the expansion began to accelerate. In the grand construction project of cosmic evolution, dark matter and dark energy serve as invisible architects, each playing a crucial role in determining what kinds of structures can exist and how they develop over time. Their influence extends from the larger scales of galactic superclusters down to the formation of individual solar systems like our own. Dark matter acts as the foundation contractor, creating the gravitational scaffolding upon which ordinary matter can build. In the early universe, when temperatures were too high for atoms to form stable structures, dark matter was already beginning to clump together under its own gravitational attraction. These dark matter concentrations created the first gravitational wells in space, invisible valleys where ordinary matter would eventually collect once it cooled enough to respond. Without this head start provided by dark matter, the universe would have remained remarkably uniform. The slight variations in density that we observe in the cosmic microwave background would never have grown into the rich cosmic web we see today. Stars would never have formed, galaxies would never have assembled, and the complex chemistry necessary for life would never have had the opportunity to develop. Dark energy, meanwhile, serves as the cosmic urban planner, determining the overall layout and evolution of the universe's largest structures. Its gentle but persistent push affects how quickly matter can fall into the gravitational wells created by dark matter. Too much dark energy too early, and structures never get the chance to form. Too little, and the universe would eventually collapse back in on itself. The timing of dark energy's dominance appears to be exquisitely calibrated. For the first half of cosmic history, gravity was strong enough to overcome dark energy's push, allowing galaxies and galaxy clusters to form and grow, but dark energy was always present, providing just enough resistance to prevent the universe from recollapsing, ensuring that there would be time for stars to shine, planets to form, and life to emerge. The most violent events in the universe often provide our clearest windows into the invisible realm that surrounds us. When galaxy clusters collide, when black holes merge, when massive stars explode in supernova, these cosmic catastrophes create natural experiments that reveal the hidden properties of dark matter and dark energy. Consider what happens when two galaxy clusters, each containing trillions of stars embedded in vast halos of dark matter, approach each other across hundreds of millions of years. From our perspective, these collisions unfold in slow motion, like a cosmic ballet performed across geological timescales. Yet the physics involved pushes matter and energy to their absolute limits. As the clusters approach, their mutual gravitational attraction accelerates them to speeds of thousands of kilometers per second. The dark matter in each cluster, interacting only through gravity, passes through the collision zone relatively unimpeded. It's like two clouds of invisible particles flowing through each other with minimal interference. But the ordinary matter tells a different story. The hot gas that fills the space between galaxies in each cluster experiences powerful electromagnetic forces during the collision. This gas slams into itself, creating shock waves that heat it to temperatures of hundreds of millions of degrees. The resulting X-ray emissions can be observed across billions of light-years of space. The spatial separation between where most of the mass is located, revealed by gravitational lensing, and where most of the visible matter ends up, shown by X-ray observations, provides direct evidence for dark matter's existence. These cosmic crashes serve as natural particle accelerators, creating conditions so extreme that they reveal the fundamental properties of invisible matter. There's something almost musical about the way the invisible universe organizes itself across space and time. The cosmic web of dark matter filaments creates a kind of three-dimensional score, with galaxies forming at the intersections like notes in a vast symphony. The oscillations in the cosmic microwave background radiation carry the echoes of acoustic waves that propagated through the early universe, frozen in time like a cosmic recording. These primordial sound waves, called Baryon acoustic oscillations, provide one of our most precise tools for measuring the effects of dark energy across cosmic history. In the early universe, before atoms could form stable structures, ordinary matter was coupled to radiation through electromagnetic interactions. Pressure waves propagated through this matter radiation fluid, creating compressions and rarefactions that moved at a significant fraction of the speed of light. When the universe finally cooled enough for atoms to form, these acoustic waves became frozen into the distribution of matter. The characteristic scale of these waves, roughly 500 million light-years, left an imprint on the cosmic web that we can still observe today. Galaxies show a slight preference for separations that correspond to this acoustic scale, like the lingering echo of primordial sound. By measuring how this characteristic scale has changed over cosmic time, astronomers can trace the expansion history of the universe with extraordinary precision. If space expands faster than expected, the acoustic scale appears larger than it should. If expansion slows down, the scale appears compressed. These measurements have provided some of the strongest evidence for dark energy's existence and constrained its properties with remarkable accuracy. As dark energy continues to drive the acceleration of cosmic expansion, it's creating a universe that will become increasingly isolated and lonely over time. The galaxies we can observe today represent a rich cosmic ecosystem, with active star formation, galaxy mergers, and the constant recycling of matter between stars and interstellar space. But this dynamic phase of cosmic evolution is temporary. Billions of years from now, the accelerating expansion will carry most galaxies so far apart that they lose all gravitational connection to each other. Star formation will gradually decline as galaxies exhaust their supplies of cold gas. Existing stars will burn out and die, leaving behind white dwarfs, neutron stars, and black holes. The universe will enter what cosmologists call the degenerate era, dominated by these stellar remnants slowly cooling in the darkness. Even farther in the future, dark energy may drive space to expand so rapidly that it overcomes not just the gravitational bonds between galaxies, but eventually even the forces that hold individual atoms together. In this scenario, called the Big Rip, the universe would end not in fire or ice, but in the complete dissolution of matter itself as space expands faster than the speed of light. Yet this cosmic loneliness paradox also reveals something profound about our current moment in cosmic history. We live during a special epoch when the universe is complex and dynamic, when galaxies are still forming stars, when the cosmic web is still evolving, when the ancient light from the Big Bang is still visible in our telescopes. The fact that we exist during this remarkable phase of cosmic evolution, when both structure and acceleration coexist, when we can observe both the cosmic microwave background and distant supernova, suggests that we are witnessing the universe during one of its most interesting and revealing periods. The relationship between quantum mechanics and dark energy remains one of the most perplexing problems in theoretical physics. When physicists attempt to calculate the energy contained in the quantum vacuum using the principles of quantum field theory, they encounter what may be the most spectacular failure in the history of science. According to quantum mechanics, empty space is filled with virtual particles that constantly appear and disappear in pairs. These quantum fluctuations should contribute energy to the vacuum, energy that would act like a cosmological constant driving the expansion of space. The problem is that when theoretical physicists calculate how much energy should be present, they get a number that's larger than the observed dark energy density by more than 120 orders of magnitude. To put this discrepancy in perspective, imagine trying to predict the weight of a feather and being off by more than the mass of all the stars in the observable universe. It's not just a small correction or a minor theoretical oversight. It represents a fundamental gap in our understanding of how quantum mechanics and gravity interact. Some theorists have proposed that most of the quantum vacuum energy might be cancelled out by some unknown mechanism, leaving only the tiny residue we observe as dark energy. Others suggest that our understanding of space and time at the smallest scales might be fundamentally incorrect. Perhaps space itself is quantized, made up of discrete units that naturally limit vacuum fluctuations. The search for a solution to this vacuum energy problem has led to some of the most exotic theories in modern physics. String theory, with its extra dimensions and vibrating loops of energy, offers potential mechanisms for cancelling vacuum contributions. Loop quantum gravity suggests that space might have a granular structure at the smallest scales, like pixels on a cosmic screen. As we push the boundaries of observation deeper into space and further back in time, we approach fundamental limits imposed by the nature of the universe itself. The cosmic microwave background represents the surface of last scattering, the point beyond which we cannot see because the universe was opaque to light. Dark energy creates event horizons beyond which information can never reach us, no matter how long we wait. These observational boundaries don't represent failures of technology or human ingenuity. They are fundamental features of cosmic architecture, built into the structure of space-time itself. Yet they also inspire us to develop ever more clever ways of extracting information from the signals that do reach us. Gravitational wave detectors have opened an entirely new window into the invisible universe. When massive objects like black holes or neutron stars spiral into each other, they create ripples in space-time itself that propagate outward at the speed of light. These gravitational waves carry information about cosmic events that produce no electromagnetic radiation, phenomena that remain completely invisible to traditional telescopes. The detection of gravitational waves from merging black holes and neutron stars has already provided new insights into the formation and evolution of massive objects in the early universe. Future gravitational wave observatories, both on the ground and in space, will probe even further into cosmic history, potentially detecting the gravitational wave background left over from cosmic inflation itself. Neutrino astronomy offers another pathway into the invisible realm. These ghostly particles produced in the hearts of stars, in the explosion of supernovae, and in the accretion disks around black holes, travel through the universe largely unimpeded by matter. Underground neutrino detectors can trace these particles back to their cosmic sources, revealing high-energy processes that remain hidden from other forms of observation. Living in a universe where the vast majority of reality remains invisible forces us to confront profound questions about the nature of existence and knowledge. For most of human history, we assumed that the material world we could see and touch represented the fundamental level of reality. The discovery that this visible universe represents only a tiny fraction of what exists challenges our most basic assumptions about what it means to know something. This situation has parallels in other areas of human knowledge. In psychology, we've learned that most mental processing occurs below the threshold of consciousness. In biology, we've discovered that most of the genetic material in our bodies consists of regulatory sequences that don't code for proteins but control how genes are expressed. In technology, most of the infrastructure that supports our digital lives operates invisibly in the background. Perhaps the universe is structured similarly, with the visible layer representing just the interface through which we interact with deeper levels of reality. The atoms and photons we can observe might be like the icons on a computer desktop, useful representations of underlying processes, but not the fundamental reality itself. This perspective suggests that the search for dark matter and dark energy is more than just a technical problem in astrophysics. It's a quest to understand the hidden architecture of existence, to glimpse the cosmic operating system that runs beneath the surface of observable phenomena. The invisible universe doesn't diminish the importance of what we can see and measure. Instead, it reveals that the visible world exists within a much richer context than we ever imagined. The complexity and beauty we observe in galaxies, stars, and planets emerge from the interplay between visible and invisible components, between forces we can measure directly and influences we can only infer. The next several decades promise to bring unprecedented advances in our understanding of the invisible universe. New space-based telescopes will map the cosmic web with extraordinary detail, revealing how dark matter and dark energy have shaped the evolution of structure across cosmic time. Advanced particle detectors will push toward ever greater sensitivity, perhaps finally capturing the first direct evidence of dark matter interactions. The James Webb Space Telescope has already begun to revolutionize our view of the early universe, revealing galaxies that formed when the cosmos was less than 1 billion years old. These observations provide crucial tests of our theories about how dark matter halos guided the formation of the first stellar systems. The upcoming Vera Rubin Observatory will survey billions of galaxies, creating the most detailed map of cosmic structure ever attempted. By measuring the shapes and orientations of distant galaxies with unprecedented precision, this survey will trace the distribution of dark matter across vast swaths of the observable universe. Underground dark matter experiments continue to push toward greater sensitivity, with next-generation detectors capable of detecting interactions so rare that they might occur only once per year in tons of target material. These experiments represent humanity's best hope of directly confirming the particle nature of dark matter. Theoretical physics continues to evolve as well, with new models that attempt to unify our understanding of dark matter, dark energy, and the fundamental forces of nature. Some of these theories suggest that the invisible universe might be even stranger than we currently imagine, with hidden dimensions, parallel realities, or forms of matter that exist in entirely separate sectors of physics. As our exploration of the invisible universe draws toward a close, we find ourselves in a position remarkably similar to that of astronomers centuries ago, peering through crude telescopes at fuzzy spots in the night sky and wondering what they might be. We have identified the invisible components that dominate cosmic evolution, measured their properties with increasing precision, and traced their influence across the history of the universe. Yet in many ways, we are still at the very beginning of understanding what dark matter and dark energy actually are. We can describe their effects, predict their behavior, and use them to explain the structure and evolution of the cosmos. But the fundamental nature of these invisible components remains as mysterious as ever. This situation is not unique in the history of science. For centuries, scientists could describe the behavior of gravity without understanding what caused it. They could predict chemical reactions without knowing about atoms. They could use electromagnetic theory without understanding quantum mechanics. Progress in science often involves learning to work productively with phenomena we don't fully understand, gradually building up the knowledge and tools needed to penetrate deeper mysteries. The search for the invisible universe represents one of the great adventures of human discovery. It pushes us to develop new technologies, new mathematical frameworks, new ways of thinking about the nature of reality itself. In pursuing these cosmic mysteries, we expand not only our knowledge of the universe, but our capacity to ask and answer fundamental questions about existence. The 95% of reality that remains hidden from a direct observation continues to beckon, challenging us to imagine new possibilities for what the universe might be. Each new observation, each theoretical breakthrough, each technological advance brings us closer to understanding the invisible majority while revealing new questions we hadn't thought to ask. Whether dark matter consists of exotic particles waiting to be discovered in underground laboratories, whether dark energy represents a fundamental property of space, or something even stranger, whether our theories of gravity and quantum mechanics need revolutionary revision, these questions will likely define the next century of cosmic exploration. And perhaps that's exactly as it should be. A universe that revealed all its secrets easily would be a disappointment, a cosmic puzzle with pieces that fit together too neatly to inspire wonder. Instead, We inhabit a cosmos that continues to surprise us, that rewards our curiosity with ever deeper mysteries, that challenges us to expand our understanding of what reality can be. The invisible universe awaits, patient and persistent, ready to yield its secrets to those bold enough to search for truth in the shadows between the stars. The invisible universe doesn't just hide from us, it actively shapes the future in ways we're only beginning to understand. As dark energy continues its relentless work of stretching space, it's writing the final chapters of cosmic evolution, determining not just how the universe will end, but what kinds of stories can be told before that ending arrives. Picture yourself standing in a vast library where the books are slowly, imperceptibly moving away from each other. At first, the change is barely noticeable. You can still reach any volume you desire, still browse the shelves, still discover new stories waiting to be read. But over time, the gaps between bookcases grow wider. Entire sections drift beyond your reach. Eventually, you find yourself isolated among just a few remaining volumes, while the rest of the library's treasures disappear into an unreachable distance. This is precisely what's happening to our cosmic library. The galaxies we can observe today represent a rich collection of stellar stories, each one a chronicle of star birth and death, planetary formation and evolution, perhaps even the emergence of life and consciousness. But dark energy is slowly, inevitably, carrying most of these stories beyond our reach. Future astronomers, living in a universe billions of years older than our own, will inhabit a much lonelier cosmos. They'll wake each day to night skies that contain only the stars of their own galaxy and perhaps a few neighbouring systems. The cosmic microwave background, that ancient whisper from the Big Bang, will have been stretched to such long wavelengths that it becomes undetectable. The evidence for cosmic expansion, for the hot, dense beginning of everything, for the existence of dark matter and dark energy itself, will have vanished beyond their observational horizon. These future scientists will face a profound challenge. How do you deduce the true nature of reality when most of the evidence has been carried away by forces you cannot see? How do you discover that your universe had a beginning when all the fingerprints of that beginning have been erased by time and distance? Yet even as dark energy erases evidence of the past, it continues to create new phenomena that reveal its presence in increasingly subtle ways. The light from distant galaxies carries within it a record of every moment of its journey through expanding space. Each photon bears witness to the gradual acceleration that has been stretching the universe for billions of years. When astronomers analyze the spectrum of light from very distant objects, they find more than simple redshift. They discover variations in the rate of that redshift, tiny changes that reflect how dark energy's influence has evolved over cosmic time. It's like reading the diary of space itself, written in the language of stretched wavelengths and delayed arrivals. These spectroscopic archaeology digs reveal something remarkable about the consistency of dark energy's behavior. Unlike ordinary matter and radiation, which become diluted as space expands, dark energy maintains constant density even as the universe grows larger. This suggests that we're not dealing with some substance that fills space, but rather with a fundamental property of space itself. Imagine trying to understand a river by watching leaves float downstream. You notice that the water's speed remains constant even though new tributaries join the flow. This would tell you something important about the nature of the current, something that goes beyond what you could learn by studying the leaves themselves. In a similar way, the consistent behavior of dark energy across cosmic time tells us something profound about the nature of space and time. The space between your fingers as you listen to this contains the same dark energy density as the vast emptiness between galaxy clusters. This isn't poetry or metaphor. It's a measured, quantified reality. Every cubic centimetre of the universe, from the core of stars to the apparent void between galaxies, participates in the same gentle expansion driven by this invisible energy. This uniformity creates one of the most beautiful paradoxes in cosmology. The force that drives galaxies apart operates everywhere equally, yet its effects are only noticeable on the largest scales. In your room, electromagnetic forces and gravity overwhelm dark energy's influence completely. But step back to cosmic distances, and dark energy becomes the dominant player in the game of cosmic evolution. It's as if the universe operates on two completely different sets of rules simultaneously. On human scales, matter clumps together, stars form, planets orbit, life emerges and evolves. These local dramas unfold against a backdrop of dark energy that remains invisible and irrelevant to the daily business of existence. But zoom out far enough, and the perspective flips entirely. What seemed like the fundamental story becomes mere detail, local fluctuations in a universe dominated by the invisible push of dark energy. Galaxies, those vast collections of billions of stars, become like dust motes carried along by currents they cannot resist. There's something almost Zen-like about the way dark energy operates. It doesn't rush, it doesn't fluctuate wildly or show dramatic variations. It simply persists, moment after moment, applying the same gentle pressure that it has maintained for billions of years. This patience, this consistency, represents one of its most mysterious aspects. Why doesn't dark energy decay over time, like radioactive elements? Why doesn't it interact with matter in ways that would change its properties? Why does it maintain exactly the energy density needed to drive acceleration without either overwhelming the universe immediately or fading into irrelevance? These questions point toward deep connections between dark energy and the fundamental structure of spacetime itself. Some theoretical physicists have proposed that dark energy might represent the lowest possible energy state of quantum fields, a kind of cosmic ground level that cannot be reduced further. Others suggest it might emerge from the geometry of extra dimensions that we cannot directly perceive. The mathematics of these theories stretches human imagination to its limits. They describe universes with 10 or 11 dimensions, where our familiar three-dimensional space floats like a membrane in a higher dimensional bulk. They propose that dark energy might leak into our world from these hidden dimensions, providing a steady source of expansion energy that maintains its strength across cosmic time. Perhaps the most remarkable aspect of our current cosmic situation is that we exist during the precise epoch when both dark matter and dark energy have become detectable. This timing isn't just fortunate, it might be fundamentally necessary for the existence of observers like ourselves. If dark energy had begun dominating much earlier in cosmic history, the universe would have expanded too rapidly for galaxies and stars to form. The gravitational collapse that creates stellar nurseries and planetary systems requires a delicate balance between the inward pull of gravity and the outward push of expansion. Tip that balance too far in either direction, and the complex chemistry of life never gets the chance to begin. If dark energy had remained weak for much longer, gravity might have eventually won the cosmic tug of war, causing the universe to collapse back in on itself before biological evolution could produce conscious observers. The window of time during which both structure formation and cosmic acceleration coexist appears to be remarkably narrow in the context of universal history. This apparent fine-tuning raises profound questions about the nature of physical law and cosmic evolution. Are we living in one universe among countless others, each with different values of dark matter and dark energy? In such a multiverse, only those rare cosmic variants with precisely the right balance would give rise to complexity, consciousness, and the ability to contemplate these mysteries. Or does the existence of conscious observers somehow influence the fundamental properties of the universe itself? This quantum interpretation of cosmology suggests that the act of measurement and observation might play a role in determining the very constants that govern cosmic evolution. Understanding the invisible universe requires thinking across scales that span more than 60 orders of magnitude, from quantum fluctuations smaller than the size of an atom to the size of a galaxy, then atomic nuclei to cosmic structures larger than galaxy superclusters. Dark matter and dark energy operate across this entire range, connecting the smallest and largest phenomena in ways we're still learning to appreciate. Quantum mechanics tells us that virtual particles constantly appear and disappear in the vacuum of space, creating fluctuations in energy density that should contribute to cosmic expansion. Yet the amount of vacuum energy predicted by quantum theory exceeds observations by an almost incomprehensible margin. This suggests that our understanding of how quantum mechanics and gravity interact remains fundamentally incomplete. Recent advances in string theory and loop quantum gravity attempt to bridge this gap by proposing that space itself has structure at the smallest scales. Perhaps space is made of discrete units, like pixels on a cosmic screen, that naturally limit the amount of vacuum energy that can exist. Or maybe the extra dimensions proposed by string theory provide a mechanism for vacuum energy to leak away into hidden sectors of reality. These theories push mathematics to its very limits, requiring concepts and tools that didn't exist even a few decades ago. They describe universes where the familiar laws of physics emerge from deeper symmetries, operating in dimensions we cannot directly perceive. They suggest that the dark energy we observe might be just one manifestation of forces that operate throughout a vast landscape of possible realities. As we approach the end of our journey through the invisible universe, it's worth reflecting on what this exploration has revealed about the nature of human curiosity and scientific discovery. We began by acknowledging that 95% of everything that exists remains invisible to us. We end with the recognition that this invisibility doesn't represent a barrier to understanding, but rather an invitation to develop new ways of seeing. The story of dark matter and dark energy is ultimately a story about the power of human imagination and ingenuity. Faced with observations that didn't match expectations, scientists didn't simply give up or dismiss the data as flawed. Instead, they proposed the existence of entirely new categories of matter and energy, invisible components that could account for what they were seeing. This willingness to accept the reality of the invisible, to work with phenomena that cannot be directly observed, represents one of the great triumphs of scientific thinking. It demonstrates that human reason can extend far beyond the limits of direct sensory experience, using mathematics and logic to infer the existence of hidden realities. The search for dark matter particles in underground laboratories, the mapping of dark energy's effects through supernova observations, the theoretical work to understand how invisible components fit into our broader understanding of physics. All of these endeavors represent humanity at its best. We are creatures who can contemplate our own cosmic insignificance, while simultaneously reaching toward truths that span the entire observable universe. As new telescopes come online, as detector sensitivity improves, as theoretical understanding deepens, we may be approaching revolutionary discoveries about the nature of the invisible universe. The next decade could bring the first direct detection of dark matter particles, or definitive measurements of how dark energy has evolved over cosmic time, or theoretical breakthroughs that unify our understanding of quantum mechanics and gravity. But even if these mysteries remain unsolved for generations to come, the search itself continues to transform our understanding of what it means to exist in this vast, strange, mostly invisible cosmos. We have learned to find beauty in uncertainty, meaning in mystery, and hope in the endless frontier of the unknown. The 95% of reality that remains hidden continues to beckon, challenging us to imagine possibilities beyond our current understanding. In that ongoing quest to illuminate the invisible, we discover not just scientific knowledge, but a profound sense of connection to something infinitely larger and more mysterious than ourselves. And perhaps that's the most important discovery of all, that we are not separate from the invisible universe, but part of it. The atoms in our bodies, the thoughts in our minds, the questions that drive our curiosity, all of these exist within and are shaped by forces we cannot see, but which determine the very possibility of our existence. The missing 95% of the universe remains the greatest mystery of our time, a cosmic riddle that challenges everything we think we know about reality. And in embracing that mystery, in accepting our place as conscious observers in an invisible cosmos, we find perhaps the deepest form of wonder available to thinking beings anywhere in the universe. The invisible universe doesn't just surround us, it flows through us, connects us, defines the very stage upon which our brief cosmic performance unfolds. As we near the end of this gentle exploration, take a moment to consider that every breath you've taken while listening has occurred within a space humming with dark energy. Every heartbeat has pulsed in rhythm with forces that dwarf our understanding, yet remain as gentle as a whisper. There's something profoundly comforting about living in a universe that refuses to reveal all its secrets at once. If cosmic reality were simple, if everything could be seen and measured and catalogued like items in a celestial inventory, would it inspire the same sense of wonder? Would we spend our evenings gazing up at the stars with the same quiet longing to understand? Instead, we find ourselves citizens of a cosmos that practices the art of mystery. It shows us just enough to keep us searching, reveals just enough to keep us humble. The galaxies spinning in their dark matter halos, the space between them stretching under dark energy's influence, the quantum foam bubbling beneath the surface of what we call empty vacuum, all of it operating according to principles we glimpse but cannot yet fully grasp. So here we are, floating together through this mostly invisible cosmos, having traced the shadows and whispers of forces that shape everything yet remain forever, just beyond our direct gaze. 95% of reality continues to dance around us, through us, within us, reminding us that the greatest mysteries often hide in plain sight. As you drift off to sleep tonight, remember that you're cradled not just in darkness, but in wonder itself, surrounded by invisible architects still writing the story of everything. Surrounded by invisible architects still writing the story of everything.